Look at your hand right now. Go ahead, actually look at it. The solid flesh, the distinct fingers, the clear boundary between where you end and the air begins. It seems undeniable, doesn't it? Your hand is there. It's real. It exists in a specific place at a specific time, made of atoms and molecules that have been there since you were born, perhaps even carrying elements forged in ancient stars billions of years ago. This is the reality we live in every single day. Objects exist. Space is a container. Time flows forward. The universe unfolds according to laws written into the fabric of existence itself. But what if I told you that in 2025, scientists made discoveries that fundamentally challenge this picture? What if the most cutting-edge physics, the most rigorous observations of the cosmos, and the most profound investigations into the nature of matter are all pointing toward the same unsettling conclusion? That the universe you think you inhabit might not be quite as solid, quite as objective, or quite as real as you've always believed? This isn't philosophy for philosophy's sake. This isn't abstract speculation divorced from evidence. These are discoveries emerging from the James Webb Space Telescope, peering into the earliest moments of cosmic history. From particle accelerators mapping the quantum realm, from seismologists listening to the pulse of Earth's interior, and from cosmologists measuring the very expansion of space itself. And together, they're painting a picture of reality that's far stranger than most of us ever imagined. The question isn't whether science will overturn our everyday understanding of existence. It's whether we're ready to accept what it's already showing us. We take for granted that the world works a certain way. When you set your phone down on a table, it stays there because the table is solid, because atoms push against atoms, because that's just how matter behaves. When you look up at the night sky, you're seeing stars that exist out there in space, distant suns burning through nuclear fusion, scattered across a vast cosmic arena that extends in all directions. This is the framework we inherit from childhood, reinforced by every interaction we have with our environment. The universe is a stage, and we are observers watching the play unfold. For most of human history, this intuition served us well. Our ancestors didn't need to understand quantum mechanics to hunt prey or build shelters. They didn't need to grasp the nature of spacetime to navigate their world. Evolution sculpted our perceptions to be useful, not necessarily accurate. And that distinction between useful and accurate turns out to be far more important than anyone suspected. Think about how you experience color. When you see something red, you're convinced that redness is a property of the object itself. The apple is red. The stop sign is red. But here's the thing. Redness doesn't exist out there in the world. What exists are electromagnetic waves oscillating at specific frequencies, particles of light bouncing off surfaces and entering your eye. Your brain takes that information and constructs the experience of red. It's a user interface, a translation of complex physical processes into something your consciousness can work with. Now extend that logic. If color is a construct of your brain rather than an inherent property of matter, what else might be constructed? Shape? Distance? The very notion of separate objects existing in three-dimensional space? Every piece of information you receive about the external world comes filtered through your senses, processed by your nervous system, and rendered into conscious experience by mechanisms we still barely understand. You've never actually touched reality directly. You've only ever interacted with your brain's model of reality. This isn't solipsism. The external world clearly exists in some form. When you close your eyes, objects don't disappear. Other people perceive the same structures you do. Physics works. But the question becomes, what is the relationship between the reality that exists and the reality we perceive? Are we seeing the world as it truly is? Or are we seeing a simplified interface designed by evolution to help us survive? Consider your computer desktop. When you see a blue folder icon, you don't believe there's actually a tiny blue folder living inside your machine. You understand that the icon is a representation, a useful fiction that allows you to interact with complex arrangements of electrons in silicon chips without needing to understand the underlying physics. The interface hides the machinery. It trades accuracy for usability. What if the same is true for everything you perceive? What if atoms and molecules, stars and galaxies, space and time themselves are not the fundamental nature of reality, but rather an interface that conscious beings like us use to navigate something far more abstract underneath? This idea, strange as it sounds, is gaining traction among physicists and cognitive scientists who study the relationship between mind and matter. The conventional story goes like this. Billions of years ago, the universe existed without any conscious observers. Particles interacted, stars formed, planets coalesced. Eventually, on at least one of those planets, chemical reactions became complex enough to support life. Simple organisms evolved into more complex ones. Nervous systems developed, brains emerged, and finally, consciousness arose as a byproduct of sufficiently sophisticated neural activity. In this view, consciousness is something the universe produces, a late-arriving feature that had no role in shaping the fundamental laws of physics. But there's a problem with this story, and it's been lurking in the foundations of physics for nearly a century. It shows up most clearly in the strange rules that govern the quantum realm, the domain of atoms and subatomic particles, where the everyday logic of cause and effect starts to break down. In the quantum world, particles don't seem to have definite properties until they're measured. An electron doesn't have a specific position until you observe it. A photon doesn't take a specific path until you detect it. Before measurement, quantum systems exist in what physicists call a superposition, a state where multiple possibilities are somehow real at the same time. And here's the truly bizarre part. The act of observation appears to collapse that superposition, forcing nature to commit to one specific outcome. For decades, physicists have debated what this means. Is measurement special? Is consciousness required to collapse the wave function? Or is there some other mechanism at play that we haven't discovered yet? The mathematics of quantum mechanics work spectacularly well. We can predict experimental outcomes with stunning precision, but interpreting what the math means, understanding what's actually happening at the quantum level, remains one of the deepest puzzles in all of science. Some physicists argue for a strictly realist interpretation. The universe, they insist, exists independently of observation. Quantum weirdness is just a reflection of our ignorance, gaps in our understanding that will eventually be filled as our theories improve. In this view, there's a true, objective reality out there, and our job is to map it as accurately as possible. Science is the process of peeling back the layers of appearance to reveal the machinery underneath. Others take a more radical stance. They suggest that the observer plays a fundamental role in bringing reality into existence, not because consciousness has magical powers, but because reality itself might be fundamentally informational. What we call particles and fields could be patterns in a deeper substrate, and measurement could be the process by which those patterns crystallize into definite states. In this picture, the universe isn't a collection of things, but a web of relationships, interactions, and information exchanges. Then, there are those who propose that space-time itself, the four-dimensional arena where physics supposedly takes place, might not be fundamental. Perhaps space and time are emergent properties, phenomena that arise from more basic ingredients, the way temperature emerges from the motion of molecules, or liquidity emerges from the behavior of water molecules. If space-time is emergent, then asking where the universe exists or when it began might be the wrong questions entirely. You'd need to look deeper, to whatever substrate gives rise to space-time in the first place. These aren't idle philosophical musings. In 2025, observational evidence began accumulating that our standard models of cosmology, refined over decades, might be incomplete or even fundamentally wrong in ways we're only beginning to appreciate. And at the heart of these discoveries lies a mystery so profound that it could reshape our understanding of what it means for anything to exist at all. The story begins with an object called QSO-1, one of hundreds of peculiar entities spotted by the James Webb Space Telescope in the distant reaches of the early universe. Astronomers call them little red dots, and from the moment they appeared in the data, they've been a source of confusion and fascination in equal measure. These objects glow with a distinctive signature in the spectrum, a V-shaped pattern indicating gas swirling at tremendous velocities around something incredibly dense and massive. For 2 years, research teams trained the telescope's instruments on these dots, gathering light across different wavelengths, analyzing the motion of matter, searching for context and explanation. And in 2025, they finally confirmed what QSO-1 actually is: a supermassive black hole with a mass equivalent to 50 million suns, sitting alone in the cosmic dawn without the usual galaxy wrapped around it. Black holes themselves aren't new to astronomy. We've known for decades that nearly every large galaxy harbors a supermassive black hole at its center. Our own Milky Way has one, a gravitational monster millions of times more massive than our sun. But even these titans are dwarfed by the galaxies that host them. Typically, a central black hole accounts for maybe 1,000th of the total mass of its galaxy. It's a significant presence, shaping the evolution of stars and gas in the galactic core, but still a relatively small component of the overall structure. QSO-1 is different. profoundly different. The black hole's mass equals nearly 2/3 of the surrounding material. It dominates the system in a way that shouldn't be possible, according to our models of galaxy formation. And when researchers analyzed the composition of the gas orbiting this behemoth, they found only hydrogen and helium, the primordial elements forged in the Big Bang itself. There were no heavier elements, no carbon or oxygen or iron. Those elements are manufactured inside stars and dispersed when stars die. Their absence suggests something shocking. This black hole formed before any nearby stars existed. The conventional narrative says that galaxies form first. Gas collapses under gravity. Stars ignite. And over time, some of those stars grow massive enough to explode and leave behind black holes. The black holes at galactic centers are thought to grow through a combination of mergers and accretion, steadily accumulating mass as the galaxy evolves. The galaxy comes first. The black hole follows, but QS01 inverts that story. Here's a black hole that appears to have assembled itself in isolation, without the galactic infrastructure that was supposed to give it birth. It's almost naked, as some researchers describe it, wrapped in only a thin envelope of primordial gas with no stellar population to speak of. Discovering even one such object is startling. Finding hundreds scattered across the early universe suggests we're missing something fundamental about how structure forms in the cosmos. One hypothesis traces back to a proposal by Stephen Hawking in 1971. He suggested that black holes might have formed in the immediate aftermath of the Big Bang, condensing directly from the primordial plasma before anything else existed. These primordial black holes would be the first structures in the universe, gravitational seeds waiting for matter to accumulate around them. Stars would come later. Galaxies would assemble over time, but the black holes would be there from the beginning. Fundamental features of the cosmic landscape rather than byproducts of stellar evolution. Another idea, known as the heavy seed scenario, proposes that enormous clouds of gas in the early universe could collapse directly into black holes without first forming stars. Under the right conditions, if a gas cloud is massive enough and the environment prevents fragmentation into smaller pieces, gravity could overwhelm all other forces and produce a black hole in one catastrophic event. This would bypass the usual stellar pathway and create supermassive black holes much faster than traditional models allow. But neither explanation fully accounts for what we're seeing. The observations don't fit neatly into existing frameworks. And that's exactly what makes them exciting. When your observations outpace your theories, when reality refuses to conform to your models, that's when genuine discovery becomes possible. That's when science has the opportunity to leap forward. The little red dots are pushing cosmology into uncharted territory. They're forcing physicists to reconsider the timeline of the early universe, the mechanisms that generated structure, and the relationship between black holes and the space around them. And they're doing it at a moment when other pillars of cosmology are also beginning to show cracks. In April 2024, a collaboration involving nearly 1,000 astrophysicists announced results that sent ripples through the scientific community. Using an instrument called the Dark Energy Spectroscopic Instrument, known as DESI, they had mapped the positions and motions of more than 6 million galaxies, stretching back through cosmic history. And hidden in that data was a signal suggesting something almost unthinkable. That dark energy, the mysterious force driving the expansion of the universe, might not be constant after all. Dark energy has been a cornerstone of cosmology since the late 1990 seconds. That's when astronomers discovered that the universe isn't just expanding, but accelerating, flying apart faster and faster as time goes on. The discovery won a Nobel Prize and upended our understanding of cosmic fate. Instead of slowing down under the pull of gravity, the universe seemed to be infused with some repulsive force that counteracts gravity on the largest scales. Albert Einstein had actually predicted something like this. In his equations of general relativity, there's room for a cosmological constant, an intrinsic energy density of empty space itself. Einstein initially introduced it to keep the universe static, before we knew the universe was expanding at all. He later called it his biggest blunder, but decades after his death, observations suggested he might have been right for the wrong reasons. The cosmological constant could explain the accelerating expansion if it represents a fixed, unchanging property of spacetime. This idea became the foundation of lambda CDM, the standard model of cosmology that describes the large-scale structure and evolution of the universe. Lambda refers to the cosmological constant, the dark energy component. CDM stands for cold dark matter, another mysterious substance that doesn't emit light but exerts gravitational influence. Together, dark energy and dark matter account for about 95% of the universe's total energy budget. We don't know what either of them actually is, but the model works. It fits observations of galaxy clustering, cosmic microwave background radiation, and supernova distances with remarkable precision, or at least it did, until DESI started hinting that something might be changing. The instrument works by measuring subtle patterns imprinted on the distribution of galaxies, echoes of sound waves that rippled through the hot plasma of the early universe. These baryon acoustic oscillations, as physicists call them, create a characteristic scale in the clustering of matter. By tracking how that scale changes over cosmic time, researchers can map the expansion history of the universe with extraordinary detail, and what they found was unexpected. The baryon acoustic oscillation scale wasn't growing at a constant rate. The expansion appeared to be slowing down, as if dark energy was weakening over time rather than remaining fixed. When the results first emerged in 2024, there was skepticism. A signal like that could easily be a statistical fluctuation, an artifact of incomplete data, or hidden systematic errors. The team reported their findings cautiously, emphasizing that more observations were needed. Then, on the 19th of March 2025, they released a much larger dataset. They had tripled the number of galaxies, adding supernova observations and measurements of the cosmic microwave background to strengthen their analysis. And the signal didn't go away. If anything, it got stronger. The same day, another independent group, the Dark Energy Survey, published their own findings that supported DESI's conclusions. Multiple datasets, analyzed by different teams using different methods, were pointing in the same direction. Dark energy might be evolving. The statistical confidence rose from 3.5 sigma to 4.2 sigma, meaning the probability that this signal is just random noise dropped from about 1 in 300 to roughly 1 in 30,000. That's substantial. That's the kind of evidence that makes physicists sit up and pay attention. But it's not yet conclusive. To claim a genuine discovery, the standard in physics requires 5 sigma confidence, about a 1 in a million chance of being wrong. The community isn't there yet. Great claims require great evidence, and the evidence, while compelling, still leaves room for doubt. But imagine for a moment that it holds up. Imagine that dark energy really is changing over cosmic time. The implications would cascade through every corner of cosmology. If the force driving the universe's expansion isn't constant, then lambda CDM, the model that has anchored cosmology for decades, would need to be replaced or fundamentally modified. All the careful calculations about the universe's past and future, all the predictions about how structure formed and evolved, would require revision. More profoundly, it would mean we don't understand what dark energy actually is. A cosmological constant is simple, almost elegant in its minimalism. It's just a number, a fixed property of spacetime that never changes. But if dark energy evolves, it becomes something far more complex and far more mysterious. Is it a field, like the electromagnetic field or the Higgs field, that can vary in strength over time? Is it a sign that Einstein's general relativity breaks down at cosmological scales? Or is it something entirely new? A phenomenon that doesn't fit into any of our existing categories. For theorists, this is exhilarating. After 27 years of working with essentially the same cosmological framework, they finally have new numbers to grapple with, new properties of dark energy to try to explain. It's like being handed a fresh puzzle after solving the same one repeatedly. The challenge is to figure out what could cause dark energy to weaken, what mechanisms could drive such evolution, and whether those mechanisms fit coherently with everything else we know about physics. Some researchers suggest it might not be about energy at all. Perhaps what we're seeing is evidence that general relativity itself needs modification at the largest scales. Einstein's theory has passed every test we've thrown at it for over a century, from the precession of Mercury's orbit to the detection of gravitational waves from colliding black holes. But maybe, just maybe, when you scale up to the entire observable universe, additional terms or corrections become important. Maybe gravity doesn't behave exactly the way Einstein described when you're dealing with billions of light years of space. Others wonder if we've been assembling the cosmic puzzle incorrectly from the start. What if dark energy and dark matter aren't separate substances, but different manifestations of a single underlying phenomenon? What if the framework we're using to interpret observations contains hidden assumptions that don't match reality? These are the kinds of questions that emerge when your best models start showing cracks, when the universe refuses to behave the way your equations say it should. The next few years will be critical. New telescopes are coming online that will gather data at unprecedented scales. The Vera Rubin Observatory, once operational, will survey the entire visible sky every few nights, cataloging hundreds of thousands of supernovae and billions of galaxies. That fire hose of data will either confirm the evolving dark energy signal or reveal it as a mirage born from insufficient statistics. Either way, cosmology stands at a threshold. Either the Lambda CDM model survives this scrutiny and we continue refining it, or we witness a paradigm shift comparable to the revolution that happened a century ago when Einstein overturned Newtonian gravity. And here's what's remarkable. This isn't happening in isolation. At the same moment, cosmologists are questioning the nature of dark energy, and astrophysicists are puzzling over naked black holes in the early universe. Geophysicists are uncovering secrets buried thousands of kilometers beneath our feet that challenge our understanding of Earth's own structure and history. For most of the 20th century, the scientific revolution known as plate tectonics transformed our view of Earth from a static sphere into a dynamic engine. We learned that continents drift, that oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones, that earthquakes and volcanoes mark the boundaries where massive tectonic plates grind against each other. Just beneath the surface, the mantle churns slowly, convecting heat from Earth's interior to the surface over millions of years. Below the mantle lies the outer core, a churning ocean of molten iron and nickel that generates Earth's magnetic field. And at the very center sits the inner core, solid metal under unimaginable pressure. This layered structure seemed well established, with sharp boundaries separating each realm. The core mantle boundary, sitting roughly 3,000 kilometers beneath the surface, was thought to be a clean division between the silicate rocks of the mantle and the metallic fluid of the outer core. But in 2025, independent investigations revealed something unexpected. These layers might be interacting in ways that blur the boundaries we thought were so distinct. The story begins with strange structures that seismologists have been mapping for decades. When earthquakes shake the planet, they send seismic waves rippling through the interior. By analyzing how those waves travel, scientists can create images of what lies below, much like a doctor uses ultrasound to see inside a patient's body. And deep at the base of the mantle, the images reveal two massive anomalies: continent-sized blobs where seismic waves slow down dramatically. These structures are called Large Low Shear Velocity Provinces, or LLSVPs for short. There's one beneath Africa and another beneath the Pacific Ocean. They're enormous, rising hundreds of kilometers from the core mantle boundary and spanning thousands of kilometers horizontally. And for years, nobody could agree on what they actually are or how they form. The conventional assumption was that LLSVPs must be hot. Seismic waves slow down when they pass through hotter material. So if these regions have lower velocity, they must be thermal anomalies, pockets of especially hot mantle rock. But here's the puzzle. Hot material should also dampen seismic waves, causing them to lose energy as they propagate. When a wave travels through warmer rock, some of its energy dissipates as heat, weakening the signal. Arwen Deus and her colleagues at Utrecht University decided to test this directly. They analyzed data from over 100 powerful earthquakes, tracking how much energy seismic waves retained as they passed through the LLSVPs compared to the surrounding mantle. If the blobs were simply hot pockets, the waves should emerge noticeably weakened. But that's not what happened. The waves maintained their strength, losing very little energy despite traversing these supposedly hot regions. This was completely opposite to expectations, and it pointed toward an explanation that nobody had seriously considered. The LLSVPs might have unusually large crystalline grain sizes. In solid rock, the size of individual mineral grains affects how seismic waves propagate. Small grains scatter and dampen waves, while large grains allow waves to pass through more cleanly. If the LLSVPs contain rock with exceptionally coarse grains, that would explain why waves slow down but don't lose energy. But how do you get large grain sizes? The answer is time. When rock sits undisturbed at high temperature and pressure, the grains gradually grow as smaller crystals merge and recrystallize. It's a slow process that requires millions or even billions of years of stability. If the LLSVPs have large grains, they must be incredibly ancient, primordial reservoirs that have sat at the base of the mantle since the earliest epochs of Earth's history. This discovery, published in January 2025, suggested that the LLSVPs are not transient features of mantle convection, but permanent anchors, stable structures that have shaped Earth's geological evolution for most or all of the planet's existence. They could be remnants of the very process that formed Earth, accumulations of material that sank to the core mantle boundary during the planet's violent infancy and have remained there ever since. Just months after this revelation, another team published findings that added a stunning new dimension to the story. These researchers studied the isotopic composition of volcanic rocks, focusing on a rare element called ruthenium. Isotopes are variants of an element with different numbers of neutrons, and each isotope carries a signature that reveals its origin and history. Ruthenium has a strong chemical affinity for iron, meaning that during Earth's formation, most of the ruthenium present would have followed iron down into the core as the planet differentiated into layers. The mantle should be depleted in ruthenium as a result, especially in the isotope ruthenium-100. But if material from the core is somehow leaking back into the mantle, perhaps rising through the LLSVPs, then volcanic rocks might contain traces of ruthenium-100 that betray this exchange. And that's exactly what the researchers found. The isotopic fingerprint was there, present in ratios that could only be explained by core material, making its way up into the mantle. It's the kind of evidence scientists dream about. A smoking gun that confirms a hypothesis once considered implausible. The core and mantle, separated by temperature, density, and chemical composition, are not as isolated as we thought. They interact, they exchange material, and the LLSVPs appear to be the conduits that facilitate this exchange, acting as stable pillars around which mantle convection organizes itself. Think about what this means for our understanding of Earth's geological activity. Plate tectonics, the engine that drives continental drift, volcanic eruptions, and mountain building, depends on mantle convection. Hot rock rises from depth, cools near the surface, and sinks back down in a continuous cycle. This circulation transports heat, recycles chemical elements, and keeps the planet's interior dynamic. If the LLSVPs are ancient, stable structures that influence how convection happens, they're not just passive features. They're active players in Earth's geology, anchors that have shaped the planet's evolution for billions of years. And this has profound implications for habitability. Earth isn't just a ball of rock floating in space. It's a living, breathing system where interior heat, tectonic activity, volcanic outgassing, and atmospheric chemistry all interact to create and maintain conditions suitable for life. The magnetic field generated by the churning outer core shields us from solar radiation. Volcanic eruptions replenish atmospheric gases. Plate tectonics recycles carbon and other elements, stabilizing the climate over geological timescales. Compare that to Mars. Mars is roughly half Earth's diameter, and its smaller size meant it cooled faster after formation. Today, Mars has no active plate tectonics, no global magnetic field, and a thin, frigid atmosphere. The planet's interior is largely frozen, geologically dead. And Mars has no life, at least none that we've detected. The contrast is stark. Earth thrives because it remains geologically active. Mars is barren because its interior went quiet. Understanding why Earth stayed active requires understanding the dynamics of the core and mantle, the processes that keep heat flowing and rock circulating even after 4.5 billion years. The discovery that the core and mantle interact, that ancient structures at the boundary between them have persisted since Earth's formation, adds crucial pieces to that puzzle. It suggests that Earth's habitability isn't just a matter of being the right distance from the sun or having the right amount of water. It's also about internal dynamics, about having a planetary interior that stays alive long enough for complex chemistry to evolve into life. Now step back and consider what these discoveries, scattered across different domains of science, have in common. Cosmologists are finding that the universe's expansion might not follow the rules we thought governed it. Astrophysicists are discovering black holes that formed before galaxies, inverting the usual order of cosmic structure. Geophysicists are uncovering ancient reservoirs deep inside Earth that challenge our picture of how planets evolve. Each discovery, taken individually, is surprising but manageable. Each one pushes the boundaries of its field without necessarily breaking them. But together, they hint at something deeper. They suggest that our models of reality, carefully constructed through centuries of observation and experimentation, might be incomplete in fundamental ways. Not wrong, necessarily. Science doesn't work by proving old ideas false and replacing them with true ones. It works by building better approximations, more accurate descriptions that account for a wider range of phenomena. Newton's laws didn't become worthless when Einstein developed relativity. They became a special case, an excellent approximation that works perfectly well in everyday situations, but breaks down at extreme speeds or in strong gravitational fields. Maybe the same thing is happening now. Maybe lambda CDM, our standard cosmological model, will turn out to be an approximation that works brilliantly for most of cosmic history, but requires modification in certain regimes. Maybe our understanding of black hole formation is incomplete because we haven't fully grasped the conditions in the early universe. Maybe Earth's interior is more complex than our layered models suggest because planets are messier, more interconnected systems than we imagined. Or maybe something more radical is going on. Maybe these disconnected anomalies are symptoms of a deeper issue, hints that our entire framework for thinking about physical reality needs adjustment. That's the possibility that haunts the edges of contemporary physics, the suspicion that we're not just missing a few details, but operating with assumptions that don't quite match the territory we're trying to map. Consider how we think about objects existing in space and time. It seems obvious that an electron is a particle, a tiny bit of matter with a definite position at each moment. But quantum mechanics insists that's not quite right. Between measurements, the electron doesn't have a position. It exists in a superposition of multiple potential positions, and only when you interact with it does it manifest in one specific location. The mathematics is unambiguous. The predictions are verified to staggering precision. But the interpretation, the question of what's actually happening, remains contentious. Some physicists embrace a many-worlds view, suggesting that every quantum measurement causes the universe to split into branches, with each possible outcome realized in a different branch. In that picture, there's no collapse of the wave function because every possibility happens. You just find yourself in one particular branch, and there are countless other versions of you in other branches experiencing different outcomes. It's ontologically extravagant, multiplying universes every time a particle interacts. But it takes the mathematics of quantum mechanics seriously, without adding extra assumptions about measurement or observers. Others prefer a more pragmatic stance. Quantum mechanics works, they say. It lets us build transistors and lasers and MRI machines. Asking what it means beyond the equations is pointless or even meaningless. Just shut up and calculate. As the saying goes, use the theory to make predictions. Test those predictions, and don't worry about the metaphysics lurking underneath. But there's a third option that's been gaining traction, especially as physicists grapple with attempts to unify quantum mechanics and general relativity. This view suggests that spacetime itself, the arena where physics takes place, might not be fundamental. Instead, spacetime could be emergent, arising from something deeper and more abstract. Just as temperature emerges from the collective motion of atoms, spacetime might emerge from relationships and correlations in an underlying substrate that has no spatial or temporal properties at all. This idea sounds bizarre, almost mystical, until you realize it's motivated by hard technical problems. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics treats fields and particles as discrete, probabilistic entities. Combining these frameworks consistently has proven extraordinarily difficult. Every attempt to build a quantum theory of gravity runs into mathematical infinities or conceptual paradoxes. String theory, loop quantum gravity, and other approaches have made progress, but none has yet produced a complete, testable theory. One promising avenue comes from studying black holes. When Stephen Hawking showed in the 1,970 seconds that black holes emit radiation and eventually evaporate, he uncovered a deep connection between gravity, quantum mechanics, and thermodynamics. Black holes have entropy, a measure of disorder or hidden information, and that entropy is proportional to the area of the event horizon rather than the volume. This suggests that the information content of a region of space is encoded on its boundary, like a hologram where a three-dimensional image is stored on a two-dimensional surface. The holographic principle, as it's called, has become central to modern theoretical physics. It implies that the number of degrees of freedom in a volume of space is limited by the area of its boundary, not by its volume. In other words, reality might be fundamentally lower dimensional than it appears. The three-dimensional space we experience could be a projection, a holographic image arising from information encoded on a distant boundary. If that's true, then asking where something exists becomes a strange question. Location in space might not be a fundamental property, but an emergent feature that arises when you're dealing with macroscopic systems made of countless particles. At the quantum level, before emergent spacetime crystallizes, the notion of position might be meaningless or context-dependent. Things wouldn't have locations until you impose the framework that creates location as a concept. This isn't just abstract theorizing. Researchers have found concrete examples in certain quantum systems where something resembling spacetime geometry emerges from the entanglement structure of quantum states. Entanglement is that peculiar quantum correlation where measuring one particle instantaneously affects another, no matter how far apart they are. Einstein called it spooky action at a distance and never fully accepted it, but experiments have confirmed it beyond any doubt. Particles can share information in ways that defy classical intuition, maintaining correlations that can't be explained by any local hidden variables. When you have many particles entangled in specific patterns, that web of correlations can encode geometric information. The more entangled two regions are, the closer they are in the emergent space. Cutting connections changes the geometry. It's as if space itself is woven from quantum entanglement, and the distances we measure are reflections of how strongly different parts of a quantum system are correlated with each other. Now apply this to cosmology. If spacetime is emergent, then the Big Bang might not be the beginning of time in any literal sense. Time itself would have to emerge from something more primitive, something that exists outside the framework where concepts like before and after make sense. The universe wouldn't have been created at a moment in time because moments in time wouldn't exist yet. The whole question of what came before the Big Bang might be based on a category error, like asking what's north of the North Pole. This brings us back to those little red dots, those supermassive black holes in the early universe that shouldn't exist, according to standard formation scenarios. If the very notion of cosmic time and structure formation depends on assumptions about how spacetime behaves, and if those assumptions break down in the extreme conditions of the early universe, then maybe we shouldn't be surprised when observations don't match predictions. We're extrapolating models into a regime where the models themselves might not apply. Similarly, the evolving dark energy signal could be telling us something about the nature of spacetime at cosmic scales. If spacetime is emergent, its properties might not be fixed. The cosmological constant might not be constant because it's not a fundamental feature of reality, but an effective description that changes as the universe evolves. The underlying substrate that gives rise to spacetime could be in a different state now than it was 10 billion years ago, and that change manifests in our observations as varying dark energy. You might object that this all sounds too speculative, too far removed from testable science. And you'd have a point. The danger in physics is always that theoretical ideas can outpace experimental constraints, leading to elegant mathematics that describes nothing in particular. But what makes these ideas worth taking seriously is that they're not arbitrary. They're motivated by genuine problems, puzzles that emerge when you try to fit together different pieces of our physical understanding. Quantum mechanics and general relativity are both spectacularly successful theories. Each one has been tested to incredible precision in its own domain, but they give contradictory answers about the nature of reality at the most fundamental level. Something has to give. Either one of them is wrong, which seems unlikely given their empirical track records, or our understanding of how they fit together is incomplete. The hunt for that missing piece, that deeper principle that unifies quantum mechanics and gravity, drives much of theoretical physics today. And it's not happening in a vacuum. Experimentalists are pushing the boundaries of what can be measured, building instruments that probe the universe at scales both vast and tiny. The James Webb Space Telescope peers back to when the cosmos was a mere fraction of its current age, capturing light that's been traveling for over 13 billion years. The Laser Interferometer Space Antenna, or LISA, planned for launch in the coming decades, will detect gravitational waves from supermassive black hole mergers across cosmic history, providing entirely new ways to test theories about the early universe and the nature of spacetime itself. Gravitational waves are ripples in spacetime caused by accelerating massive objects. Their discovery in 2015, a century after Einstein predicted them, opened a new window on the universe. But ground-based detectors like LIGO can only sense relatively high-frequency waves from stellar mass black holes and neutron stars. LISA, floating in space with laser arms millions of kilometers long, will be sensitive to much lower frequencies, the kind produced when supermassive black holes spiral together and merge. If you're enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. These mergers might reveal whether those little red dots really are primordial black holes from the dawn of time. If black holes formed before galaxies, Their mergers should produce gravitational wave signals with distinctive characteristics that differ from what you'd expect if galaxies formed first. LISA will either confirm the standard picture or force us to revise it. Either outcome advances our understanding, but one of them would trigger a revolution in cosmology comparable to what happened when we discovered the universe was expanding in the first place. Back on Earth, geophysicists continue mapping the planet's interior with increasing resolution. New seismometer networks, improved data processing algorithms, and better computational models allow them to see finer details of the structures beneath our feet. The discovery that the core and mantle interact challenges textbook geology, but it also opens new research directions. If material cycles between the core and mantle, what does that mean for Earth's chemical evolution? How does it affect the magnetic field? What role did it play in making Earth habitable when so many other rocky planets in the universe likely remain barren? These questions matter beyond academic curiosity. Understanding what makes a planet capable of supporting life has direct implications for the search for life elsewhere. We know of thousands of exoplanets now, worlds orbiting other stars. Some of them sit in the habitable zone where temperatures allow liquid water. But is that enough? Do you also need plate tectonics to stabilize the climate? Do you need a magnetic field to protect against radiation? Do you need a certain size, a certain composition, a certain history of formation to maintain geological activity over billions of years? The more we learn about Earth's interior, the more we realize how many factors had to align to produce a living world. That doesn't mean life is rare. The universe is vast, and even if the conditions are stringent, there are hundreds of billions of galaxies, each containing hundreds of billions of stars. The sheer number of opportunities makes it seem likely that life has emerged elsewhere, but it does mean we can't assume that rocky planets in habitable zones automatically become inhabited. The full recipe for life might be more complex than we thought, and here's where the different threads start weaving together. Cosmology tells us about the large-scale structure and evolution of the universe. Astrophysics explores the formation and behavior of stars, planets, and black holes. Geology investigates Earth's history and dynamics. Quantum mechanics describes the behavior of matter at the smallest scales. Each discipline has its own domain, its own methods, its own vocabulary, but reality doesn't respect these boundaries. The universe is one interconnected system, and phenomena at different scales influence each other in ways we're only beginning to appreciate. The atoms in your body were forged in stars that exploded billions of years ago. Those stars formed from gas clouds enriched by even earlier generations of stars. The heavy elements that make up Earth, that compose the rocks beneath your feet and the iron in your blood, all came from stellar nucleosynthesis and supernova explosion. You are literally made of stardust, reconstituted into a form capable of contemplating its own origins. But go deeper. The protons and neutrons in those atoms are made of quarks, held together by the strong nuclear force. The electrons orbiting atomic nuclei are fundamental particles, as far as we know, with no internal structure. They exist in quantum superpositions, spread out in probability clouds, until something interacts with them. And that interaction, that process we call measurement or observation, involves other particles, other quantum systems, in a chain of correlations that extends outward to include you, the observer, as part of the quantum description. You can't cleanly separate the observer from the observed at the quantum level. The act of measurement is a physical interaction, and both the measuring device and the measured system must be described quantum mechanically. This isn't some mystical insight about consciousness affecting reality. It's a technical statement about how quantum systems work, but it does have philosophical implications that are hard to ignore. If observation is just a physical interaction, then what makes some interactions special? Why does measuring an electron's position collapse its wave function while other interactions don't? Or do all interactions collapse wave functions? In which case the whole universe is constantly collapsing and there's no fundamental role for measurement at all. These are the questions that fuel debates about quantum foundations, and there's no consensus answer. The Copenhagen interpretation, taught in most textbooks, basically sidesteps the issue by drawing a line between the quantum world and the classical world of everyday experience. Below that line, superposition and probability. Above it, definite outcomes and determined properties. But where exactly is that line? At what scale does quantum weirdness give way to classical behavior? Nobody knows, and attempts to specify it precisely always seem arbitrary. The many-worlds interpretation eliminates the line by making everything quantum. There's no collapse. Every possibility happens. The universe branches, and you go along one branch, while other versions of you go along others. It's conceptually clean but ontologically expensive, requiring you to accept the existence of an unfathomable number of parallel realities. Then there are objective collapse theories, which modify the equations of quantum mechanics to include spontaneous, random collapses that happen without observation. These theories predict that quantum superpositions naturally decay into definite states when systems become large enough, providing a physical mechanism for the transition from quantum to classical. The collapses would be incredibly rare for individual particles, but become frequent in macroscopic objects made of countless particles. Some versions even suggest that consciousness might be related to these collapse events, though that remains highly speculative. Each interpretation makes different assumptions about what's real and what's just a calculational tool. And because they all reproduce the same experimental predictions in the regimes we can currently test, there's no way to definitively choose between them based solely on evidence. This frustrates many physicists, who prefer their science to deliver clear, unambiguous answers. But it's also a reminder that science is always interpretation, always a process of fitting models to observations. The data doesn't speak for itself. We have to decide what it means. The same ambiguity shows up in cosmology. When we look at the cosmic microwave background, that faint glow left over from when the universe became transparent, about 380,000 years after the Big Bang, we see patterns. Tiny fluctuations in temperature, deviations from perfect uniformity by only 1 part in 100,000. Those fluctuations were the seeds that grew into galaxies and clusters of galaxies. The patterns tell us about the conditions in the early universe, the distribution of matter and energy, the relative amounts of ordinary matter, dark matter, and dark energy. But interpreting those patterns requires a model. You have to assume something about how the universe evolved, about what kinds of processes were important, about which physical quantities remained constant and which changed over time. Lambda CDM makes specific assumptions. Dark energy is constant. Dark matter is cold and collisionless. The initial fluctuations follow a particular statistical distribution. Given those assumptions, you can calculate what the cosmic microwave background should look like, and the match between calculation and observation is stunning. Except now the assumptions might be wrong. If dark energy evolves, Lambda CDM doesn't work anymore. You need a new model with different assumptions. And that new model might predict subtle differences in the cosmic microwave background that we haven't noticed yet because we've been looking through the wrong lens. Or it might predict differences that only show up in observations we haven't made yet, at scales or epochs where the standard model worked fine, but the new model diverges. This is how science progresses. You build a model that fits the data. You test it with new observations. Sometimes it passes and your confidence grows. Sometimes it fails and you refine or replace it. The process is messy, iterative, and never truly finished. There's always another decimal place of precision, another regime of extreme conditions, another unexpected phenomenon that forces you to rethink what you thought you knew. And through it all, there's this nagging question. Are we describing reality as it actually is, or are we just building increasingly sophisticated models that match observations without necessarily capturing the underlying truth? Science can tell you what happens. It can predict the outcomes of experiments with remarkable accuracy. But can it tell you why? Can it reveal the fundamental nature of existence, or is it forever limited to constructing useful fictions? Interfaces that let us navigate a reality we can never directly perceive? This is where physics meets philosophy, where empirical investigation bumps against questions about the limits of knowledge itself. And it matters because how you answer these questions shapes what kinds of explanations you find satisfying, what kinds of theories you pursue, what you think science can ultimately achieve. If you're a realist, you believe there's an objective reality out there, independent of observers, and science is the process of mapping it. The map will never be perfect, but it can get better and better, asymptotically approaching truth. Quantum mechanics might seem weird, but that's just because reality is weird at small scales. Our intuitions, shaped by evolution to handle medium-sized objects at moderate speeds, mislead us when we venture into unfamiliar territory. The goal is to overcome those intuitions and see the world as it really is. If you're an instrumentalist, you think talk of objective reality is overblown. Science gives us tools for prediction and control, and that's all we need. Whether there's a reality behind the observations is either unknowable or irrelevant. Theories are instruments, not pictures. They're judged by their utility. not their truth. As long as quantum mechanics lets us build better computers and cosmological models, let us understand the evolution of structure in the universe, the metaphysical questions about what's really real can be set aside. And if you're drawn to something like the interface theory mentioned earlier, you think the distinction between reality and appearance is more subtle than either realism or instrumentalism acknowledges. Yes, there's something out there, but what we perceive is filtered, processed, and constructed by the architecture of our minds and senses. The interface is real, and it's shaped by both the external world and the internal workings of perception, space, time, objects. These are features of the interface, not necessarily features of the underlying territory. None of these positions can be decisively proven or refuted. They're frameworks for interpreting evidence, lenses through which you view the scientific enterprise, but they're not equally useful in all contexts. Realism motivates the search for deeper explanations, the conviction that there are answers to be found if you dig hard enough. Instrumentalism keeps you focused on what you can actually measure and predict, preventing you from getting lost in speculation. Interface theory reminds you that observation is always mediated, that the act of perceiving shapes what you perceive. The physicists working on little red dots and evolving dark energy and Earth's interior structure aren't typically worried about these philosophical distinctions. They're focused on data, on building models, on testing predictions. But implicitly, their work embodies a commitment to the idea that the universe is comprehensible, that patterns and observations reflect something deeper than chance, that puzzles have solutions, even when those solutions require overturning established frameworks. And sometimes, the puzzles lead you to question not just specific theories, but the entire conceptual apparatus you've been using. That's where we might be now, not at the end of physics. As some prematurely declared at the turn of the 20th century, before relativity and quantum mechanics upended everything, but at a moment when multiple anomalies are accumulating and the standard models are showing strain. The little red dots suggest our understanding of structure formation in the early universe is incomplete. The evolving dark energy hints that the cosmological constant might not be constant. The core mantle interactions reveal that Earth's interior is more dynamic and interconnected than we realized. Quantum mechanics still lacks a universally accepted interpretation. Attempts to quantize gravity keep running into obstacles. Dark matter remains undetected despite decades of searching. Dark energy's nature is a complete mystery. These aren't failures of science. They're the growing pains of a discipline pushing against the edges of the known. Every answered question opens new ones. Every solved puzzle reveals deeper layers of complexity. And that's exactly how it should be. If we ever reached a point where there were no more mysteries, where every observation fit neatly into a complete and final theory, science would be finished. Not successful, finished, done, over. There would be nothing left to discover, but we're nowhere near that point. If anything, the more we learn, the more we realize how much we don't know. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, and we've examined only the tiniest fraction of them in any detail. We've barely explored our own solar system beyond a few robotic missions and crewed flights to the moon. We understand the fundamental forces at one level, but can't explain why there are four of them, why they have the strengths they do, or how they unify at high energies. We know that ordinary matter, the stuff made of protons, neutrons, and electrons that constitutes everything we can see and touch, accounts for less than 5% of the universe's total energy. The rest is dark matter and dark energy, and we don't know what either one actually is. We have names for them, mathematical descriptions of their effects, but no direct detection, no confirmed particles, no fundamental understanding of their nature. And even focusing just on the ordinary matter, we don't understand how it organizes itself into living systems. We know life is chemistry, that biology emerges from the interactions of molecules following the laws of physics. But we can't yet explain how non-living chemistry transitions into living biology, how self-replicating molecules evolved into cells, how cells organized into multicellular organisms, how nervous systems gave rise to consciousness. Consciousness might be the deepest mystery of all. You are aware. You have subjective experiences. There's something it's like to be you, a first-person perspective that seems utterly different from the third-person objective descriptions of physics and chemistry. How does that happen? How do particular arrangements of matter and energy produce the sensation of redness, the feeling of pain, the experience of joy? Why is there anything it's like to be a brain processing information when there's presumably nothing it's like to be a rock or a river? Some philosophers and scientists argue that consciousness is an illusion, a trick the brain plays on itself. But that seems to miss the point. Even if your sense of being a unified self is constructed rather than fundamental, the fact of experience remains. Something is aware of the illusion. Something has the subjective impression of continuity and identity, even if that impression doesn't correspond to any single persistent entity. The hard problem of consciousness, as philosopher David Chalmers called it, is explaining why there's subjective experience at all, not just how the brain processes information. And here's where everything loops back to the beginning. If consciousness is fundamental, if awareness is a basic feature of reality rather than an emergent property of complex information processing, then the whole picture changes. Maybe the observer isn't incidental to physics. Maybe the reason quantum mechanics gives a special role to measurement isn't because consciousness collapses wave functions, but because reality itself is fundamentally experiential, and what we call physical laws are patterns in how experiences relate to each other. This sounds mystical, and it edges into territory that makes many scientists uncomfortable. But it's not necessarily unscientific. If consciousness is fundamental, there should be principles governing how it behaves, regularities that can be studied and tested. Some researchers are exploring whether quantum effects in the brain might play a role in cognition, whether entanglement or superposition could contribute to the binding problem or the integration of information across different brain regions. The evidence is preliminary and controversial, but the questions are legitimate. Others approach consciousness from the perspective of information theory, treating it as a measure of integrated information in a system. The more interconnected and interdependent the parts of a system are, the more conscious it is. By this standard, your brain has high consciousness because different regions communicate extensively and influence each other in complex ways. A thermostat has minimal consciousness because its information processing is simple and isolated. A single atom has essentially none because there's no internal structure to integrate. This quantitative approach makes testable predictions about which systems should be conscious and to what degree. It suggests that consciousness isn't binary, not something you either have or don't have, but a spectrum. And it implies that consciousness could be much more widespread in the universe than we typically assume, present to varying degrees in any system that integrates information, though perhaps only in vanishingly small amounts, unless the system reaches a certain threshold of complexity. Whether any of this is correct remains uncertain. Consciousness research is still in its infancy, struggling with fundamental questions about how to even measure or define its subject matter. But the fact that serious scientists are grappling with these questions at all represents a shift. A few decades ago, consciousness was considered off-limits, too subjective and fuzzy for rigorous investigation. Now, it's a legitimate field of study, with journals, conferences, and research programs at major universities. The same is true for many of the topics we've explored. Primordial black holes were fringe speculation until telescopes started finding evidence for them. Evolving dark energy would have been dismissed out of hand until multiple independent datasets pointed in that direction. Core mantle interaction was assumed to be negligible until isotopic signatures proved otherwise. Science advances by taking seriously what the data shows, even when it conflicts with established models. And the data keeps surprising us. The universe refuses to be simple. Every time we think we've got a handle on how things work, new observations reveal additional layers of complexity. This might frustrate our desire for tidy explanations, but it's also exhilarating. It means there's always more to discover, always deeper questions to ask, always new frontiers to explore. So where does that leave you? The person reading these words, trying to make sense of your existence in a cosmos that seems increasingly strange the more we learn about it. You're still here, still reading, still experiencing the flow of thoughts and sensations that constitute your conscious life. The discoveries we've discussed don't change that immediate reality. Your hand is still in front of you. The world still seems solid and persistent and real. But maybe now you hold your assumptions a little more lightly. Maybe you recognize that the solidity is a useful interface, not necessarily the deep truth of what matter is. Maybe you appreciate that the laws of physics we've discovered are descriptions of patterns, not explanations of why those patterns exist. Maybe you wonder whether the universe you inhabit is the same as the universe itself, or whether you're experiencing a particular slice, a projection shaped by the specific way your brain and senses interact with whatever lies beneath. These aren't just abstract intellectual exercises. They shape how you think about your place in the cosmos, about what it means to be human, about how seriously to take your perceptions and intuition. If the universe is fundamentally quantum, if spacetime is emergent, If consciousness has a role we don't yet understand, then the mechanistic picture of humans as biological machines implementing algorithms breaks down. Not because there's anything supernatural, but because the categories we're using, machine, algorithm, matter, might not be fundamental. They might be high-level descriptions that work well in certain contexts, but obscure deeper realities. It also changes how you think about the future. If dark energy is evolving, the fate of the universe becomes less certain. The standard prediction is that accelerating expansion will continue forever, eventually leaving each galaxy isolated in an increasingly cold and dark cosmos, as stars burn out and black holes evaporate over unimaginable timescales. But if dark energy can change, maybe that future isn't inevitable. Maybe the expansion will slow, halt, even reverse. Maybe there are cycles, phases of expansion and contraction playing out over timescales that dwarf the current age of the universe. If primordial black holes exist, if structure can form in ways we haven't imagined, if the relationship between matter and spacetime is more fluid than we thought, then the possibilities multiply. The universe could be far older than we believe, with histories that predate the Big Bang as we understand it. There could be regions of space where the laws of physics differ from what we observe locally, where particles and forces we've never encountered play dominant roles. And if consciousness is fundamental, or at least more widespread than we assume, then the universe might be full of observers, entities experiencing reality in ways we can't begin to imagine. Not just biological organisms on planets like Earth, but perhaps more exotic forms of awareness, associated with different substrates, different configurations of matter and energy, different interfaces onto the underlying reality. None of this is certain. Much of it is speculative, extrapolations from fragmentary data, and incomplete theories. But that's the nature of science at the frontier. You work with the evidence you have, you build models that fit, you make predictions and test them, and you remain open to being surprised. The history of science is a history of surprises, of discoveries that force people to revise their understanding of what's possible. A few centuries ago, the idea that Earth orbits the Sun was heretical. The notion that living things evolved from simpler forms was scandalous. The concept that space and time are relative rather than absolute seemed absurd. Quantum superposition, black holes, the expansion of the universe. All of these were met with skepticism or disbelief when first proposed, and all of them are now established facts, confirmed by overwhelming evidence. What will the next century bring? What discoveries are waiting just beyond the current limits of observation and theory? We don't know, and that's part of what makes the scientific endeavor so compelling. Every generation thinks it's on the verge of completing physics, of answering the final question, and every generation discovers that the questions only multiply, that reality has more layers than anyone suspected. The little red dots shining in the data from the James Webb Space Telescope are mysteries today. In a decade, we might understand them completely, fitting them neatly into an expanded cosmological model, or they might remain puzzling, signposts pointing toward revisions we haven't yet imagined. The dark energy signal could strengthen to 5 sigma and beyond, forcing a paradigm shift in cosmology. Or it could fade as more data comes in, revealed as a statistical fluctuation. After all, the core mantle interactions could rewrite our understanding of planetary dynamics, or they could turn out to be less significant than current evidence suggests. Science is uncertain. That's not a weakness. It's a strength, the willingness to follow evidence wherever it leads, to abandon cherished theories when they no longer fit observations, to live with ambiguity and incomplete knowledge. These are the virtues that allow science to progress. Dogmatism is the enemy of discovery. Curiosity, skepticism, and openness are the tools that let us navigate the unknown, and you get to participate in this journey. Not necessarily as a professional scientist, though if that's your path, these are exciting times to pursue it. But as a person living in an age where the boundaries of human knowledge are expanding faster than ever before, where telescopes and particle accelerators and seismometers and quantum computers are revealing new facets of reality on a regular basis, you get to witness the process of discovery, to watch as mysteries unfold and paradigms shift. More than that, you get to embody the mystery. You are a conscious observer in a quantum universe, a pattern of matter and energy that somehow gives rise to subjective experience, a local concentration of complexity that emerged from simpler components over billions of years of evolution. You are the universe becoming aware of itself, experiencing its own existence through your eyes, your thoughts, your sensations. That's not poetry. It's literal. The atoms in your body were forged in stellar furnaces. The molecules that compose your cells follow the same quantum mechanical laws that govern everything else. The electrical impulses flickering through your neurons are physical processes, no different in principle from lightning or radio waves. And yet, somehow, those processes produce consciousness, the inner light of awareness that makes you who you are. How that happens remains one of the deepest mysteries in science. But the fact that it does happen, that you exist as a thinking, feeling entity capable of pondering your own existence and the nature of reality, is perhaps the most extraordinary fact of all. You are not separate from the universe studying itself. You are the universe studying itself, one tiny part of the cosmic whole that has somehow acquired the ability to ask questions about the rest. And those questions matter. They drive progress. They inspire investigation. They push us to build better instruments, develop better theories, explore further into the unknown. Every discovery we've discussed in this journey began with someone asking a question that others might have dismissed as too difficult, too speculative, or too far beyond current capabilities. What are those red dots in the early universe? Is dark energy really constant? Do the core and mantle exchange material? Each question opened a path that led to unexpected answers and new mysteries. The next breakthrough could come from anywhere. It might emerge from data already collected, waiting for someone to notice a subtle pattern that everyone else missed. It might require new technology, telescopes more powerful than Webb or particle accelerators, beyond anything currently operating. It might come from a young researcher asking a naive question that opens up an entirely new way of thinking about an old problem. Or it might come from synthesis, someone recognizing connections between disparate fields that no one saw before. The interplay between quantum mechanics and gravity, the relationship between consciousness and information, the link between cosmological evolution and the nature of time. Science doesn't progress in neat, isolated tracks. It's a web of interconnected investigations, and sometimes the biggest insights come from seeing how pieces fit together. What we know for certain is that the universe is far stranger than our ancestors imagined, and probably stranger than we currently imagine. The solid, objective reality of everyday experience is a useful approximation, an interface that lets us navigate the world. But underneath that interface lies something more abstract, more mathematical, more thoroughly weird. Quantum fields fluctuating in a space-time that might itself be emergent. Information encoded holographically, consciousness playing a role we don't yet understand. Multiple interpretations, all consistent with observations, pointing in different directions about what's ultimately real. You don't have to choose. You can hold multiple possibilities in mind simultaneously, recognizing that our current knowledge is provisional, subject to revision as new evidence arrives. The important thing is to remain curious, to ask questions, to resist the temptation to settle for easy answers, when reality keeps demonstrating that easy answers don't do it justice. The cosmos is a grand experiment, and you're part of it. Every time you observe something, every time you think about your observations, every time you wonder why things are the way they are, you're participating in the universe's ongoing project of understanding itself. That's a remarkable thing. That's a privilege and a responsibility. The more we learn, the more we realize how much remains unknown. And that's not a problem to be solved. It's the permanent condition of any finite intelligence confronting an infinite reality. So keep looking up at the stars. Keep asking questions about the nature of existence. Keep wondering whether the universe you perceive is the universe itself, or whether there are depths below depths, realities behind realities, mysteries within mysteries, extending forever beyond our grasp. The journey toward understanding might never end, but that doesn't make it futile. It makes it eternal, an endless adventure of discovery that gives meaning to the brief flicker of consciousness you call your life. We stand at a threshold, perhaps on the verge of paradigm shifts that will reshape cosmology, redefine our understanding of matter and space-time, and force us to reconsider what we mean by existence itself. Or perhaps not. Perhaps the anomalies will resolve, the standard models will be refined rather than replaced, and the universe will prove slightly less strange than current evidence suggests. Either way, the investigation continues. Either way, we keep pushing forward, driven by the fundamental human need to understand, to know, to make sense of the mysterious cosmos in which we find ourselves. That's the story of science. That's the story of human curiosity. And that's the story we're all living, whether we realize it or not. The universe revealed itself to you at birth, presenting you with an interface of colors and shapes and sounds. Over time, you learn to navigate that interface, to predict what happens when you take certain actions, to build a mental model of how things work. And now, if you followed this journey through quantum mechanics and cosmology and deep Earth dynamics and the nature of consciousness, you have a slightly expanded model, one that acknowledges the gaps, the mysteries, the places where our certainty runs out and wonder begins. Hold on to that wonder. It's the engine of discovery, the force that drives us to look deeper, think harder, question more thoroughly. The universe doesn't owe us easy answers. It doesn't owe us any answers at all, but it offers them anyway to those patient and persistent enough to seek them out. And every answer, without exception, opens new questions that lead further into the labyrinth of reality. That labyrinth has no exit because there's nowhere outside reality to exit to. We're inside the mystery. We'll always be inside it, but that's okay. That's better than okay. It means the journey never ends. It means there's always more to explore, always another horizon to cross, always another layer of understanding waiting to be uncovered. And as long as conscious beings exist anywhere in this vast cosmos, that exploration will continue, driven by the same impulse that drove our ancestors to wonder about the lights in the sky, and that drives us now to send telescopes into space and particle beams circling underground, and questions probing the very foundations of existence. The little red dots will be explained. Dark energy's nature will be determined. The relationship between core and mantle will be mapped. Quantum mechanics will be interpreted or replaced by something deeper. Spacetime's origin will be understood. Consciousness will be accounted for. Each mystery will yield, eventually, to investigation and insight. And each solution will reveal new mysteries, new puzzles, new frontiers, stretching endlessly into the unknown. That's not a flaw in the system. That's the system working exactly as it should. Reality is inexhaustible. Knowledge is infinite, and we, fragile patterns of matter briefly gifted with awareness, get to participate in the grandest endeavor imaginable. The universe coming to know itself, one discovery at a time, one question at a time, one moment of understanding at a time. So here we are, at the end of this particular exploration, but nowhere near the end of the journey. The cosmos stretches out before us, vast and strange and beautiful, full of secrets waiting to be uncovered. The tools are ready. The questions are sharpening. The data is accumulating. And somewhere out there, in telescopes and laboratories and minds not yet born, the next revolution is brewing. The next paradigm shift is preparing to upend everything we think we know. When it comes, we'll adapt. We'll revise our models. We'll expand our conceptual frameworks. We'll find new interfaces for navigating reality, better approximations that capture more of the underlying truth. And we'll keep going, because that's what conscious beings do. We ask questions. We seek answers. We marvel at the complexity and beauty of the universe that created us, and that we, in turn, are slowly coming to understand. The stars are still there, shining in the night. The quantum fields are still humming with possibility. The earth is still churning beneath your feet, and you are still here, still conscious, still capable of wonder. That's enough. That's everything. That's the foundation upon which all science builds. The irreducible fact of awareness in a cosmos that somehow permits, and perhaps even requires, observers to exist. Whatever comes next, whatever discoveries await in the decades and centuries ahead, we'll face them with the same tools that brought us this far: curiosity, rigor, openness, and an unwavering commitment to following the evidence wherever it leads. The universe may be strange, but it's comprehensible. Reality may be layered and complex, but it's investigable. And we, improbable as our existence might be, are equal to the challenge of understanding it. One mystery at a time, one breakthrough at a time, one moment of awestruck recognition at a time. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.